here in the Smash build folder. And this is because we are going to use Smash completely autonomously, independently on JETSCAPE now. And let's make the yes/no poll. When you have Smash compiled, press yes. And let's see how many people have compiled Smash. Okay, I already see some people successfully running Smash. What about compiling? Did you create a yes/no poll? Am I even online?
Dima, there's a poll that's going on the first question that you asked. So it takes a little bit of time.
Yeah, good.
So
good.
It's now at 25 yeses and 6 nos. So I think we give them a few more minutes and then.
Absolutely. The compilation is taking some time, depending on your computer number, of course.
We're at 32 yeses and 6 nos.
6
and
no's.
I just
If you
want to
have some
ask,
problems, post it on the Slack chat.
I just want to ask what the 6 no's means. Is that means it's still compiling, or does that mean that there's been an error? And so you should, if you have an error, you should just type in the Slack. Just copy paste your error in the Slack channel.
Okay, so for those people who were able to compile Smash, try to run Smash ---- help. First of all, it gives you the idea of possibilities how you can run Smash with different command line options. And this is one of the reasons why I'm doing this outside of JETSCAPE, because in JETSCAPE, Smash is part of JETSCAPE. You can put all the things in the configurations with the JETSCAPE that you can put in standalone Smash, but you cannot just run Smash with this nice command line options. And many things are passing by when you are completely in the JETSCAPE environment. If you run Smash version, you should probably see something like 1.8. This is the recent version of Smash.
So we're now at 41 yeses and 5 nos. And that's been stable for a bit. So what do you want to do?
Then let's go further. I'm assuming that people who have managed to compile Smash were also trying to run Smash ---- help and get the results. And you should probably see the list of command line options that Smash can take. Then Smash ---- version should give 1.8 and some additional information. And well, just running Smash is going to run Smash with the default configuration. And the default configuration is a gold-gold collision at 1.23 AGV. So this is a very low energy compared to what you might be used to. This is not RIC, not LAC. This is hardest collision energy and GSI. So in the end, we want to run Smash as a hadronic afterburner. This is not what Smash is doing by default, so we are going to have to configure it. You can configure Smash in two ways. One is by the config file, and by default the config file is called config.yaml. You can edit the config file, or you can create your own config file and run Smash with your own config file like this. There is this -- input file option, and then you put your own YAML file. Yes, I think slides are posted in the Indico page. Oh, the slides should be on the previous session. They are posted on the Indico page. Yeah, okay, so this is way one to configure Smash, and way two is by the command line options. If you have some config file, then Smash is reading configuration from this config file. And then if you give additional option, then it is overriding what you have in the config file. So let's say if you have n time of the simulation 100 Fermi, and then you add this -- config n time 40 Fermi, then you will have 40 Fermi simulation. It is overriding what you have in the input file. Let's go further for a moment and look at the content of the input file. Here is the config YAML file of Smash. You can see here version 1.8. This is intentional to have Smash running with the config for the right version, because sometimes there are outdated options or there are options that haven't been implemented. So this is just ensuring that Smash version is matching. Then the next thing, you can see logging and this default info. It means that Smash, when it is run, it is printing out lots of things in green color. And when you ask default info, it's printing just reasonable essential info. If you put something like warn or error here, it's going to print much less. So for example, if you're running Smash on the cluster, you just don't want to print too much. So you put warn here instead of info. People are already asking how to set collision energy in the config file. So look at this MODI, the last one, the last part of the configuration. MODI, collider, and one of the parameters here is EKIN. This is kinetic energy of the collision, and it's 1.23. It means 1.23 GeV. So this is going to be gold and gold collision at 1.23 AGV, because this EKIN means it's in the lab frame. And you can also set square root of S here. One way to learn how to type the square root of S correctly is to just type some nonsense here and then run Smash, and Smash is going to complain and tell you what kind of options you have here. We are not going to type square root of S. Okay, so there is a question what 79 and 118 means. Let's look at this more carefully. MODI, collider. Collider, I was telling in the lecture, you can run Smash in different ways. And collider means you are going to initialize two nuclei, like two actual nuclei with protons and neutrons, and they are going to collide. You can also run Smash as a box or as an afterburner or as a sphere. And here in this collider, there is setting for projectile. And for projectile, you set which particles are going to constitute projectile. Usually for nuclei, it's protons and neutrons. Then you can see this funny 2212. 2212 is the code, is the standard particle data group code for proton. So you can see that there are 79 protons and 118 neutrons, because this is standard code for neutrons. And this is exactly the gold nucleon, 79 protons and 118 neutrons, and the same number of protons and neutrons in the target. I want to draw some attention to the other parts of the configuration. Number of events, this n events, it's going to be only one event by default. The end time is the finishing time of the simulation. This is Fermi over C. So it's going to finish at 200 Fermi over C. And output interval is how often it prints out results with particles, for example. And important for us is it's going to print particles, and it's going to print in some Oscar 2013 format, which is just a text format. It's human readable. So if you have run smash, just default smash output, then you can go to the latest data 0, data 1, data 2, and so on folder, and look at the files there. And one of the files is going to have the extension something like Oscar 2013. And you can look at the content of this file. It's simply a particle list. You can see that there is some header, and then just information about particles: the time, spatial coordinates, mass, energy, and momentum, and the code of the particle. So from this code, I can see that it is a pi 0 because 111 is the code of pi 0. And then the just number, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and charge of the particle. So, okay, you have looked at it in a simple text way. We don't want to analyze the text output. Of course, it is possible. You can write a script, analyze the text output, but I would suggest to do analysis in a simpler way for our purposes and create a root output. Okay, so to have the root output, you have to modify the config file. So the next thing you have to do is to modify the config file. I suggest to put in some events, some number of events. Let's do 50. And in addition to Oscar 2013 format, add this root format. Now Smash is going to print results in two formats simultaneously. So you will have at the same time the Oscar output and the root output. And well, with this new config, let's run Smash. If you need this to copy this config, then you can find it in the instructions. Let me post this text instructions on chat once again. It was on the chat, but I think it's really useful to have it once again. Okay, so if you
Dima?
the instructions, here are the instructions for copying all the kinds of code that you cannot copy from the presentation.
Dima?
Mm-hmm.
Can you hear me?
Yes.
Somebody has typed into the first line of your Google Doc, of your Excel sheet. You might need to refill that again. Yeah, so just a comment to everybody: if you when you start filling out the Google Doc, please find a blank line and fill in your name there, and then fill out, yes or no.
Okay, that is just a little glitch. Oh, I don't remember what was there.
Dima, I can take.
Okay, yeah, if you can help me with that, that would be really nice. And in the meanwhile, well, I see that a lot of people were actually able to generate the root output already, and no, not that many people. Okay, so few were able to generate the root output. It takes some time to run. It takes a few minutes to generate results, especially if you run Smash for the first time. It's going to tabulate all the cross sections. It's going to take time.
While we're on this, can I ask, are these tasks like prerequisites to the next task, or can people skip some of these?
This is basically just learning how to deal with the Smash configuration. And in the next tasks, some things will be, you just do it on your own. So I'm not telling what to put in the configuration. You just do it on your own. So this is learning how to deal with the configuration. Yeah, that was a good question. What is this frozen Fermi motion? So first of all, what is Fermi motion? The nuclei are Fermi spheres. So in coordinate space, nuclei are just spheres, right? But in momentum space, nucleus is a quantum object, and protons, for example, are subject to Pauli blocking because they're all fermions. So if you put all the protons with zero momentum in the nucleus, they are not going to sit there. And it means that they have to have some momenta. And these momenta are called Fermi momenta. Because with zero momentum, this Pauli blocking is just not allowing nucleons to sit in a nucleus with zero momentum. Then the question is, what kind of momenta you give to the nucleons? And you give them momenta in a Fermi sphere. But then if you give nucleons momenta in a classical transport code, then nucleus is just going to fly away. And Fermi motion frozen means that nucleons know that they have Fermi momenta, but they only start using it when they start colliding. So a nucleus is kept intact. That's a little trick that transport codes use, and it's quite a smart trick. If you are using your QMD, GBU, whatever, and run it without potentials that keep nuclei together, then your only option is to go for frozen Fermi motion or no Fermi motion at all. Okay, so assuming you were able to run Smash with the root output, now let's actually look at this root output. And that we are going to do with the root. Now you have two options. If you have root outside of Docker, you can open root outside of Docker and use tbrowser. If you don't have root outside of Docker, then you follow these instructions. Let me see. Let me explain what these instructions are. So the first thing is to run root. This is root minus L. Minus L means that it's running without its graphical logo, and root is just starting root. Then with these three guys, you're opening the root file you have generated. It can be data1 here or next number of the folder. Just choose the latest folder you have generated. Then open the file particles root. Then root file is a special binary construction. Experimentalists know it. If you haven't used root file before, it's an interesting format of the file created by CERN and originated from René Brun. And it's efficient in many ways. It's efficient in the way it stores data, and it's efficient in the way it allows you to read data, and it's nice in the sense that you can open it and look in a graphic way what's inside. And it uses the concept of trees and branches. So this is because of the root name. The objects inside of the root file are called trees, and particular variables, let's say, are going to be called branches. So in this way, you open one particular tree in the root file. In Smash output, there is only one tree in the root file. The tree is called particles. So you're trying to get the tree called particles from the root file, assign it to the tree object, And the next thing is going to print you out the content of this tree. So you will see what kind of variables were printed out by Smash. So let's say press yes if you were able to see some output from this scan, and then you see what the variables are there. The alternative to doing these three things are just opening T browser. With that, I'm assuming that you are familiar with the T browser, and just clicking on the particles tree. Okay, so let me look once again at how people are progressing. So some people managed to generate root output. Some didn't really manage to generate the root output. Ah, okay, there are a lot of spaces. Okay. So I see that a lot of people have actually generated the root output. So let's proceed one step further. Let's draw the rapidity distributions. We are going to draw the rapidity distributions for protons and pions by using just one command. As long as you have loaded this tree, then you can draw things with just one command in root. This is command draw. It takes several parameters. The first parameter is what you are going to draw. You can see the mathematical expression for P0 and PZ. This is the expression for rapidity. P0 is the energy of the particle. PZ is the Z component of momentum of the particle. This is the definition of rapidity. The question here is, how do you know that you have to put P0 and PZ here? Because when you print the scan, particle scan, then you see that the branches, the names of the branches where you have energy and Z component of momentum are called like this. So formally, this is names of the branches in the tree in the root file. Every variable is called branch in this concept. You have root file and trees and branches, so you have the whole garden in the end. That was the concept. Then the next thing that you put here, the next parameter, is this PDG code equals to 2212. This is code of proton, and this whole thing is cutting on the PDG code. So it means that we are going to draw rapidity distribution only for protons. And the last parameter is the drawing parameter. It just tells, show me error bars. And it is showing error bars as square root of number of counts in the histogram. And in this way, you save it as a picture. So you will have rapidity spectrum of protons at which energy? At the one that you have run Smash. It's gold-gold collisions, 1.23 GeV in the lab frame. Then, what is C1? This is a good question. So root keeps some hidden variables. And when you do this particles draw, it actually tells you that a canvas with the name C1 was created. So this is a name of the root object, a graphical canvas. And you call it to this graphical canvas to be saved to the file. Then you do exactly the same thing, but now instead of cutting for proton PDG code, you cut for pions. This is the code for pi plus, pi 0, and pi minus. So it either has to be pi plus or pi 0 or pi minus. And then you get the rapidity spectrum of pions in some other picture. Now we want to put them both on the same histogram, on the same picture. Then you just repeat the same commands, except in the last graphic option, you put this little same option, and this is what does the job. And if you do it just like this, you will have two lines of the same color, and it's really hard to distinguish what's protons and what's pions. Now, to make one of the things red, just execute this and save them in the rapidity spectra comparison. And after that, you should be able to get this kind of picture. And let me see how far you are. Are you getting to this picture? So I see that some people manage to compare proton and pion rapidity distributions, but not everybody is there yet. So I think I have to wait for a minute and try to make sure that more people get there. Oh, somebody doesn't have root. Wait a second, you have root. You have root in your Docker environment. It is not really possible that you don't have root. Root is the part of Docker environment. So when you have generated the spectra, now you can see this plot. What's funny about this plot? Yes, you can see rapidity on the x-axis. You can see number of counts from all your 50 events on the y-axis. It is not normalized, it's from all events. And you can see two rapidity spectra, which look reasonable, symmetric around 0. That is good. Now you're trying to guess what is protons and what is pions. So now I actually want you to answer the question, is it yes or no? So if yes, then red is pions, blue is protons. If no, then blue is pions, red is protons. Could you please reset the poll if there was some lost poll?
Poll is reset.
Mm-hmm. So yeah, let's see what people think. Is it pions red, protons blue, or pions blue, protons red? Remember, this is gold, 1.23 AGV.
Can you remove the highlight? Yeah, thanks.
Okay, let me wait for a minute here and see how the progress is going.
Can you see the results of the poll?
I cannot see the results of the poll. One thing I can see is my table file. And
okay, so the
in
poll
table,
says
I can see how far some people have reached.
Okay, so I'm looking at the poll. The poll is now says 17 yeses and 10 nos.
Okay, so people are divided here. It's some people think red are pions, blue are protons. Some people think in the opposite way.
I just want to say that on my screen, it's the blue really appears as black. So just letting you know.
Yeah, it's
somebody want you go back to one place last slides.
This one.
And I should mention that all the slides are available on the Indico. I think all these slides are available, were posted on yesterday's part of the timetable, right?
Mm-hmm. Yes.
We're at 21 yeses and 13 nos.
Okay, I think we can stop at this moment and go further. So those who have answered yes, this is correct. First of all, you can see that the blue or black rapidity distribution is wider. And well, this is because particles that collide sit at higher rapidities. So the actual answer is blue are protons and red are pions. And to get the actual mid rapidity number, you have to divide by 50 because this is 50 events. This was not normalized. So yeah, we skip through installing ParaView. This will be optional. And now we go to the part 2. Now you have learned how to configure Smash, how to generate root output, and how to analyze the root output. Now let's use this for something exploratory. I was telling yesterday that Smash is the last part that you run after the hydrodynamics as a hadronic afterburner. So I have prepared some sampled particles from the hydrodynamics just to start the last stage. And we are going to run Smash as a hadronic afterburner. To do this, download the sampled particles I have generated. This is central gold-gold collision, 19.6 GeV with smooth initial conditions. I was generating it from music hydrodynamics using the ISS sampler from Chun, and energy density at particularization was 0.26 GeV per Fermi cubed, which is the default in this case. Look into the instructions for the link, download this archive with the particles. It's not very large, it's something like 6 megabytes. And then go to the build folder. Yeah, download this this archive to the build folder where you are working, untar it, and you should get the file with the name sampled particles 0. This is what we are going to use to run Smash as an afterburner. And let me give you a minute to finish that. The link is in the instructions. You go to the instructions. Let me actually post the link just for making it easier. So kinetic and chemical freeze-out, and I'm copying the link and pasting it. Where is it? School. So this is the link to the file with the generated particles from the hydrodynamics. And when you have downloaded this, then we proceed to configuring Smash in a way that runs as an afterburner with the particles we have given it. If you are looking into the instructions, that we are at point 4 exploring chemical and kinetic freeze-out, and in the part Smash simulation. This is where you might want to copy the code of the config file. Somebody argued that about the baryon stopping. protons being red and pions being blue. Well, you can actually easily check what is what. I might be mistaken. You can easily check because you have generated 3 pictures. You have generated the plot for protons separately, for pions separately, and the plot together. So just compare it to what you have generated separately. And well, maybe I'm just wrong. By running SMASH as an afterburner, I mean that we take the generated particles from the hydrodynamics and make SMASH run starting from these particles. So once again, running SMASH as an afterburner, let me go to this slide. Well, you take particles from the hydrodynamics here, feed it into SMASH, and then let them collide, let the resonances decay, let particles form new resonances. Those resonances also collide and decay. And this rescattering is called hadronic afterburner. Some people say hadronic rescattering, or transport stage, hadronic afterburner, hadronic rescattering. Yeah, so this means running SMASH as a hadronic afterburner. And to run SMASH as a hadronic afterburner means you download the sample particles that I generated from music hydrodynamics at 19.6 GeV. And then you prepare the config for SMASH. Now, when many people have downloaded the file, let me explain what's in the config. It is somewhat similar to the previous config, except in the MODI, instead of collider, there is list right here. And it means that it just takes the list of particles you give it. Then number of events is now 100. And you can see that the output is not only particles, but there is also output of collisions. And both are in root format. That's the difference. So for this config file, go to the instructions and just copy the whole config file and put it in this config SMASH tutorial afterburner YAML file. And run SMASH. So if you were able to run it successfully, and it takes few minutes actually, so it's probably going to be like 4 minutes. Then you have generated the results of SMASH simulation. Then at the same time, when this simulation is running, just to save time, open a different tab and generate the same kind of simulation, so from the same particles, but now we want to ask SMASH to not collide anything. So only resonances are going to decay. And this will be the second type of simulation. So we start from the same particles, the same hydrodynamics, the same particles, and then we have 2 SMASH simulations. One is going to be with collisions, and one is going to be without collisions. To configure simulation without collisions, this is this additional option that you put right in the config file as, let's say, last 2 lines. You say collision term, no collisions true. So now we're going to have 2 results of simulations. One is with collisions, just normal SMASH with full power, and one is only resonance decays. And with that, we can finally ask some conceptual questions, what we are doing and what's going on. So let me see, are people able to generate run smashes? I don't really see many people being able to run smashes in Afterburner. Is there some showstopper, or it's just taking time? Let's make another poll. We don't have that much time. So let's make a poll. Do you know what chemical and kinetic freeze outs are? If you know what it is, then press yes and think for 2 minutes about the definitions, and in 2 minutes post them in the chat. If you don't know what they are, it's okay, just say no and look at the definitions people post in the chat.
I just cleared out the poll and people are voting.
So some people are complaining about problems with copy and paste. It seems that it is happening because of your text editor. Okay, I already see some people posting something about chemical and kinetic freeze out.
So I'm seeing right now 28 yeses and 7 nos.
Yeah, excellent. Already what you are posting are already excellent answers. That is very good. So I see two types of answers right now already. A chemical freeze out is that yields numbers of particles are not changing. And at the same time, people are saying chemical freeze out is when inelastic reactions cease. And for kinetic freeze out, the spectra of particles are not changing anymore. And another definition is the elastic reactions cease. However, so there is a contradiction in this definition. So let's actually look at the results of the SMASH simulations. We have run, hopefully, maybe it's still running, but we are running SMASH with all the reactions on and without any kind of reactions, only resonance decays. So if we get the same spectra, that means that kinetic freeze out already happened at the moment of transition from hydro by definition, right? Because the spectra didn't really change whether you run SMASH with all the collisions or all the resonances. And if spectra have changed, then kinetic freeze out happened somewhere in the SMASH phase. You can also count particles, and if the number of particles, let's say number of pions, hasn't changed between running SMASH without collisions and with collisions, then it means that chemical freeze out happens already before SMASH was run. Yeah, I have this in the question number 2, but I think we just don't have time to think and post in the chat. So now look at your results and just say what you are seeing. Are you seeing chemical and kinetic freeze out, or both, or none of them? after analyzing the results of your simulation. And there is also a bonus, so for everybody to think and post in the chat, is we have done 2 simulations. We have printed out particles and collisions. Just based on this kind of simulations, I think you can suggest a lot of ideas. And just try to think and suggest ideas outside of just chemical and kinetic freeze-out. Just suggest any ideas what it would be interesting to analyze and say based on simulations, comparing with all the reactions in SMASH and without anything.
By the way, Dima, you have 32 yeses and 8 nos. Should we close the poll?
Yeah, I think yes. I think a lot of people have answered already in the chat, and there were really good answers already. So let me see, were people able to finish the afterburner simulations? Okay, so I see a lot of checks. So the afterburner simulations are finished. Now let's analyze the results. Look at the spectra and try to make your conclusions. You have both particles and collisions. And the interesting part is that if you look at the collisions, the inelastic reactions are not really finished. So there are a lot of inelastic reactions happening in SMASH. But at the same time, the number of particles of many species, of pions, of kaons, also partly for protons, are not really changing much. So it turns out that the definitions of the freeze-out are contradicting with each other. So if you say chemical freeze-out is when inelastic reaction cease, it's one moment. And when you say chemical reactions, chemical freeze-out is when number of particles is not changing, it's a different moment. So you have to be really careful about the definitions of chemical and kinetic freeze-out. So right now you are on yourself. You have the results of the simulations. You know how to analyze them, how to make spectra. And looking at the instructions, you also know how to look at the collisions. So now look at the spectra, look at the collisions, and well, you just have 5 minutes, but this is also homework. Try to think and make conclusions out of the results of your simulations. And I'm leaving these conclusions on your own. I'm not making conclusions myself. It is your job to analyze the results and make conclusions. And they can also be non-trivial conclusions. I think that in this kind of simulations, there are still results where you can think, obtain something new, and even write a paper. One such idea may be if you look at the resonances. LHC has only recently measured resonance production. So if you look at the afterburner, how resonances are produced, look at the reactions, look at the results with rescattering and without rescattering, then you can actually extract something new. But what new is up to you to think. So think, you can post on the chat, you can also just think for yourself. You can write me an email if you wish. If you have a great idea for the paper, write me an email. And well, just continue thinking. What kind of things you can say about chemical freeze-out, what kind of things you can say about kinetic freeze-out, what changes if you look at collisions, at particles. How much the hadronic rescattering changes the yields and spectra. In the end, if hadronic rescattering doesn't change anything, why do you need hadronic rescattering, right? So also look what kind of observables are changed by the hadronic rescattering. So here I'm really encouraging you to think on your own and design your own idea of what you want to compare, what kind of spectra you want to look at, what kind of reactions you want to look at. And for the root commands for that, you find them all in the instructions. If you find some interesting, unexpected, non-trivial results, then you can either post them on the chat or write me an email. And here in the presentation, I have a little bonus, how to generate nice visualizations. Apparently, we are not making that. So you can just look it up in the instructions if you are interested. This is a little bonus of how to make visualizations like this, like I'm showing on the slide. For that, you just have to generate the proper output and open it in ParaView. That's the nice part of Smash, that you don't have to design visualizations yourself. Just generate the right file. So I'm stopping here on analyzing the results. This is your homework, and this is homework not only for doing, but for thinking. Try to think what you can learn from the simulations you have done. Try to think about chemical and kinetic freeze-out. And we have to be finishing now. So let's make the final poll. And the final poll is, have you learned anything from the hands-on session? Press yes, no. No is definitely okay. And if you have learned something, just write 1 or 2 things in the chat that you have actually learned.
I just want to clarify, Zoom chat or Slack chat?
Oh, Slack chat. Yeah, not in the Zoom chat.
So we are at 27 yeses and 1 no.
Mm-hmm. Well, if yes, then write in the chat what you have learned. No is good. It means that we have honest people who are not afraid to say no. And maybe there is somebody who actually puts no there because he or she knew everything about Smash already.
Yeah, I just want to mention in this context that we have a channel called Comments. If you have some ideas on how this, these lectures, general comments on the lectures, you should definitely put it there. So just find the channel called Comments, and then you can type it there. So we're at 35 yeses and 1 no.
There is actually a comment in the welcome session about this hands-on session. Essentially, it said the real-time compilation and calculation sometimes make it more difficult for people to follow, I guess.
This is definitely true, but look at the high energy physics and what it is. To a large extent, both from the theoretical and experimental side, is just a lot of software packages. New students are coming, you have to learn 100 software packages. Well, this is life today. Like 10 years ago, you come to experimental physics, you just have to learn Jant and root, and you spend 3 years for that for sure. For theory right now, it seems that you also have to learn packages, hydro, transport, or whatever simulations you are doing, and you have to get acquainted with some software package. So it's just, well, unavoidable that lots of efforts are going into compilation.
And I'll add that having somebody live to assist you with these compilation issues is critical. And some people would run into these on their own without help, and then that would be the end.
So I'm reading the comment by, I'm gonna not say the name properly.
Agnieszka.
Agnieszka. Yeah. So I just want to ask: is the 1 week we spent before installing everything that definitely didn't help? And if you want to speak now, you can unmute your microphone and comment as well.
Hello, can you hear me?
Yes,
Yeah.
Go ahead.
No, I just mean the installations during the hands-on sessions, because I actually know how to run Smash and also how to use root, but to be able to get to the analysis stage, there was 30 minutes of installations for me. And I think this could have been done before.
30 minutes? This is how, what did you do that you got 30 minutes of installation?
I followed your instructions. And the instructions.
This Smash installation on one core took like 4 minutes maximum on one core.
All right, I have no idea. This is inside Docker. Maybe that is the case as well. I don't know, but okay. I agree this took a really long time, but I think this is also very easy instructions to follow. So this could have been sent to us in advance, maybe with some office hours that you could hold for us to be ready to actually do the analysis. And altogether, I think the session is really great, and I like your exercises and the homework, and I like that you're not giving us answers. So the entire idea is perfect. It's just that installation really took a lot of time. And
I actually know what could have gone wrong on your side. So when you were compiling Smash, this makes Smash -J2. If you type make -J2, then you could have wasted a lot of time.
Actually, what took a lot of time was get Smash SH. That was the.
Oh, then your internet must be really slow. Oh no, I
well,
don't know.
Yeah, I don't know. Yeah, so sorry, because I really like this session and I like the exercises. So I think this is a perfect idea, but the problem is that people's connections are different and people's laptops are different, and to get these technical stuff out of the way before we do actual physics exercises, I think would be a little bit better. But overall, the feedback from me is that I love these hands-on sessions. They're great. Okay, thank you.
That's interesting, because on my laptop it was taking rather fast. I would like to really hear some feedback from people, maybe under your message, for those who also had to use like half an hour for getting Smash, because that is far too much.
I just want to point out, I think also to that to everyone, that this is of course the first time we are trying something like this, to do a hands-on session online, and so I think we're learning as well. And I think probably as the school progresses, I'm hoping that the other instructors are also here and watching all this, and things will be a little bit different maybe as the week goes on. But I agree also with Dima a little bit. I think that just the get Smash, that probably indicates something wrong with the internet connection. But it's probably something we could have
from some other people.
Mm-hmm.
Because this is far too much. It's not supposed to be like that.
So people can find this comment on the welcome channel, and a couple of other people, I think, have also agreed to this.
Mm-hmm. I see. So maybe the downloading Smash, when people are downloading Smash from German server, maybe the German server was sluggish, but yeah, that's still weird. And Smash is not really so bulky in terms of space. But okay, let me make the final word. So I see that most people learned basically just how to run Smash. This is good, but try to go here to the slide where you analyze the results and try to think. And think of not only of the technical part that you have done, but think of what you have analyzed and what you can also analyze from exactly what you have generated. And I think there is some physics there in chemical and kinetic freeze-out that you will be able to think through and understand better. And maybe even if you go deeper, maybe you can even write a paper about something.
So Dima, do you have anything else, or should we start closing the session?
Yeah, let's start closing the session. So do this thinking about physics and further analysis as a homework.
All right, everybody. So we are losing people now. We've dropped below our 100 participants. Are there any burning questions that anybody needs to ask that were not addressed in the Slack? If you already asked the question in the Slack and you had replies, but those replies did not address your question, please raise your hand. We use the raise hand button on Zoom. I'm not seeing any hands. So as always, please continue asking questions in the Slack if you have more issues. And I'm going to now close the session. And we will move tomorrow to JETS and jet and medium interactions. So see everybody back at the same time tomorrow. All right, bye.
Bye, thank you.
Bye.
Thank you.